What happens inside a microprocessor's clock cycle? Imagine a tiny conductor orchestrating a symphony of electrical signals inside a microprocessor. Every movement, every node, depends on a precise timing signal called the clock. Now, let's uncover what actually happens during each beat of this clock. A microprocessor uses a clock signal that looks like a square wave, oscillating between high and low states at a fixed frequency. This clock acts as a metronome, dividing time into small chunks called clock cycles. Each cycle is like a heartbeat that keeps all parts of the processor working in harmony. When the clock signal rises from low to high, it triggers a series of events inside the processor. First, flip-flops and registers, which are tiny storage units, capture data present on their inputs. This is like pressing a button to save a piece of information at just the right moment. All these storage elements update their states simultaneously, making sure data moves smoothly without errors. Once the data is stored, signals travel through the processor's combinational logic circuits. These circuits perform calculations, logic operations, or address computations. Think of it as the processor doing math or figuring out where to find data next. The signals need to settle and stabilize here before the next clock pulse to avoid mistakes. The clock cycle also marks the steps for executing instructions. First, the processor fetches an instruction from memory using the program counter, which points to the next command. Then, it decodes the instruction to understand what needs to be done. Next, the arithmetic logic unit, or ALU, performs calculations or logical operations. If needed, data is read from or written to memory during this time. Finally, the processor writes back the results into registers or memory, completing one instruction cycle. The clock signal makes sure all these steps happen in order, preventing signals from arriving at different times. It distributes the clock through a network inside the chip, designed to minimize delays so everything stays synchronized. Every clock cycle also consumes power because internal transistors charge and discharge. Faster clock speeds mean more power and heat, which limits how fast a processor can run. That's why engineers work hard to design efficient clock distribution networks and find the right balance between speed and power. In embedded systems, understanding what happens during each clock cycle helps optimize performance and power use. Techniques like clock gating turn off parts of the processor when not needed, saving energy. So, inside each clock cycle, the processor's internal components work together in a timed dance. The clock signal triggers data storage, logic operations, and instruction steps, making sure everything happens in a neat, predictable order. This timing is what keeps digital devices running smoothly and accurately.